Hello students. So until the last class we had discussed about the basic idea of a single movable pulley and a single fixed pulley. The unit A was already covered, and in this second unit we are now left out with the topics of the combinations of pulleys. Now it is quite obvious to you, as you have learned from the previous discussion, that if we have only a single fixed pulley, the maximum that we can do is change the direction of effort to a convenient pulley. And if we have only a single movable pulley, yeah, we do get some multiplication in the force, but that is again only twice. That is, if I apply an effort of 10 newtons, the maximum I can lift is a load of 20 newtons. But there may be situations where we need to lift even heavier loads, even greater amount of force has to be overcome. So what do we do for those situations? For those situations we need something which is the combination of pulleys. That is to say, we need more than one pulley system. So this is one of the ways of the combination of the pulleys. So another combination that we will do is the block and tackle system. In this combination, what we do is we take a number of movable pulleys, and along with that there is another fixed pulley. So here we have the 3 movable pulleys, and attached with that is one fixed pulley. How do you draw the diagram? So one end of this lowest movable pulley is attached to the rigid support, the other end is attached to the block. For the second pulley, one end is again attached to rigid support, the other end to the consequent block. For the third pulley, one end to the rigid support, the other one to, it goes round the pulley like this, so that you can apply the effort here. Now if you want even more movable pulleys, then instead of allowing this string to pass like this, you can attach this end of the string to another block, which will again increase the number of the pulleys that we have in hand. Now, as you already know, that effort is always applied at the free end, and at this end we will apply the load which is acting in the downward direction. This load has to be lifted. And if you can see from this setup that the load here, L, is being balanced by 2 forces in the upward direction, which is 2T1. Why 2 times? This tension and this tension, both of them add in the upward direction to balance the load in the downward direction. For the second pulley, that is for this pulley, this tension T1 is balanced by 2 tensions here. So tension T1 is 2 times T2, right? Similarly for the third one, tension T2 is equal to 2 times tension T3, and tension T3 is now equal to effort. So what we have to do is we can write all of them in terms of one tension. That is to say, from this expression we can find out that tension T1 is load divided by 2. From this expression, therefore, tension T1, if I in place of that I put L by 2, then L by 2 is 2T2, so which implies that tension T2 is L by 2 squared. Similarly, if you substitute it here, you will get tension T3 is L by 2 cube. But tension T3 is also by effort. And what is the formula for mechanical advantage? The formula goes like this: it is equal to load divided by effort. So load is equal to, in this case, the load is 2 to the power 3 times tension T3, and effort is T3. So it gets cancelled. What remains is 2 to the power 3, that is equal to 8. So as we discussed, we see that we get a mechanical advantage which is many times greater than what we are used to getting with one movable or one fixed pulley. And this mechanical advantage of equal to 8 means that this acts as a wonderful force multiplier, which means that suppose if we apply an effort of simply 10 newtons, just 10 newtons, how much load can we lift? Mechanical advantage is 8. This is the amount of load we can lift. So just by applying a simple effort of 10 newtons, we can lift a load of 80 newtons. That is why we say that this acts as a force multiplier. This complete setup acts as a force multiplier. And one thing, I don't know if you have noted it, that we wrote here that mechanical advantage, we found it out, in fact, is 2 to the power 3. But 3 is also the number of movable pulleys in my case. In my case, I have 3 movable pulleys. So from here you can write down a general formula that whenever you have a combination of a number of movable pulleys with one fixed pulley in this particular manner, the mechanical advantage is given by the formula 2 to the power n, where n denotes the number of movable pulleys. So mechanical advantage is equal to 2 to the power n, where n denotes the number of movable pulleys whenever I have a setup like this. And what is the velocity ratio? The velocity ratio, it turns out to be 2 to the power n also, or in this case 2 to the power 3 as well. Because if you see that velocity ratio, what is it? It is basically, velocity ratio is basically the displacement of effort by displacement of load. And if you see here that whenever the load is displaced by say x units, these portions of the string they get displaced by 2x unit. When this portion gets displaced by 2x unit, these portions of the string get displaced by 2 times 2x unit. And so on, it goes on increasing. Therefore, finally the displacement of effort is equal to 2 to the power n times x units, and displacement of load is x units. So it turns out to be 2 to the power n. So for lifting the load by a distance of only say x units, you have to make the string at the end of the effort go down by an amount 2 to the power nx. And since velocity ratio, mechanical advantage are equal, the efficiency eta is equal to 1 or 100%. But obviously this is the case for a ideal machine, because we know in real machine there will be certain weights of the pulley parts and there will be frictions between their bearings, due to which reason the actual efficiency in the real world will be less than 1 or less than 100%.